The readings for Lecture 7, 4.1 and 4.2, starting with functions and scoping. We've already used a number of built-in functions, such as max and abs in Figure 4-1, which was earlier. Don't worry about it. The ability for programmers to define and then use their own functions as if they were built in is a qualitative leap forward in convenience. Function definitions. In Python, each function definition is of the form def, name of function, list of formal parameters, body of function. For example, we could define the function max_value by the code def define space max_value, then parenthetically x, y, colon, if x is greater than y, colon, return x, else, colon, return y. Def is a reserved word that tells Python a function is about to be defined. The function name, max_value in val in this example, is simply a name that is used to refer to the function. The PEP8 convention is that function names should be in all lowercase with words separated by underscores to improve readability. And it is important to keep them all lowercase so they won't get confused with classes and stuff. The sequence of names within the parentheses following the function name, x, y, in this example, are the formal parameters of the function. When the function is used, the formal parameters are bound, as in an assignment statement, to the actual parameters, often referred to as arguments. In fact, pretty much always referred to as arguments. I've never heard them called actual parameters. Of the function invocation, also referred to as a function call. For example, the invocation, or function call, max_val, and then parenthetically 3, space 4, binds x to 3 and y to 4, or assigns 3 to x and 4 to y, in other words. The function body is any piece of Python code. There is, however, a special statement, return, that can be used only within the body of a function. Because a function call is an expression, and like all expressions, it has a value. That value is returned by the invoked function. For example, the value of the expression max_val, parenthetically 3, 4, times max_val, parenthetically 3, 2, is 12, because the first invocation of max_val returns the integer 4, and the second returns the integer 3. And so, meaning that this will be equal to, in a sense, what it outputs. If you set up two function calls and try and perform arithmetic on them, that's what you're actually performing arithmetic on, is the output of each function given the arguments that you passed in, right? Note that execution of a return statement terminates an invocation of the function. To recapitulate, when a function is called, 1. The expressions that make up the actual parameters are evaluated. In other words, the arguments, as they're always called. I'm surprised to see them being called this. The expressions that make up the arguments are evaluated, and the formal parameters, otherwise always just called parameters, of the function are bound to the resulting values. For example, the invocation max_val, then in parentheses 3 plus 4, space z, will bind the formal parameter x to 7, because this expression will be evaluated, 3 plus 4, so x will become just 7. And the formal parameter y to whatever the value the variable z has whenever the invocation is executed. And of course, if you haven't defined z and assigned a value to it earlier in the code, then this will just return an error. 2. The point of execution, the next instruction to be executed, moves from the point of invocation to the first statement in the body of the function. 3. The code in the body of the function is executed until either a return statement is encountered, in which case the value of the expression following the return becomes the value of the function invocation, or there are no more statements to execute, in which case the function returns the value none. If no expression follows the return, the value of the invocation is none. 4. The value of the invocation is the returned value. And 5. The point of execution is transferred back to the code immediately following the invocation, the function call. Parameters allow programmers to write code that accesses not specific objects, but instead whatever objects the caller of the function chooses to use as actual parameters, as arguments. This is called lambda abstraction. Figure 4-3 contains a function that has 3 formal parameters and returns a value. Call it result, such that the absolute value of result to the power minus x is greater than or equal to epsilon. Okay. So, def find underscore root. Define the function, name it find underscore root, and set the parameters as x, power, the variable power, and a variable named epsilon. And here's our definition of the function. Our comment, find interval containing the answer if x, whatever's passed in as argument here, if that x is less than 0, and whatever's passed in as argument to our power parameter, power modulo 2 is equal to 0, meaning it's even, return none. A comment explains negative number has no even-powered roots. Set the value of a variable low equal to the result of passing in -1 and x to the min function, and set a variable called high equal to the result of passing in 1 and x to the max function. Comment explains use bisection search. Create a variable ants and set that equal to the result of evaluating the expression high plus low, these two variables we just made, divided by 2, then while the absolute value of ants to the power minus x is greater than or equal to epsilon, if ants to the power is less than x, then update the value of our low variable equal to the ants variable, or else update the value of the high variable to equal to the value of our ants variable. Finally, update the value of ants to high plus low divided by 2 and return the final value of ants. This is another function for finding roots. This guy's just obsessed with finding roots. Figure 4-4 contains code that can be used to test whether find underscore roots works as intended. The testing function test underscore find underscore root is about the same length as find underscore root itself. To inexperienced programmers, writing test functions often seems to be a waste of effort. Experienced programmers know, however, that an investment in writing testing code often pays big dividends. It certainly beats sitting at a keyboard and typing test cases into the shell over and over during debugging, which is, by the way, the process of finding out why a program does not work and then fixing it. Notice that because we are invoking test find root with 3 tuples, that is, sequences of values, in parentheses, of length 3, one call checks 27 combinations of parameters. Finally, because test find root checks whether find root is returning an appropriate answer and reports the result, it saves the programmer from the tedious and error-prone task of visually inspecting each output and checking it for correctness. We return to the subject of testing in Chapter 8. Finger exercise. Use the find root function in figure 4-3 to print the sum of approximations to the square root of 25, the cube root of -8, and the fourth root of 16. Use 1/1000th as epsilon. Finger exercise. Write a function is underscore in that accepts two strings as arguments. See, he calls them arguments too. Elsewhere, it's like, and returns actual parameters. That accepts two strings as arguments and returns true if either string occurs anywhere in the other and false otherwise. Hint, you might want to use the built-in CTURE operator in. Finger exercise. Write a function to test is in. Here's some code to test find root. Test find root, which has these three parameters: x vals, powers, and epsilons. And for x in x vals, whatever number is passed in here as argument for the index variable looping through it, for x in vals, and then nested for p in powers, nested for e in epsilons. Update the value of our variable result equal to the result of calling the find root function with x, p, and e passed in as arguments, and that will be the index variables that we just created here, iterating through each of these numbers that are passed in here, So find the result of what the find root function would return if that number at that step in the iteration for each of these was passed in as the three arguments. If result is equal to none, then update the value of a variable val equal to the string no root exists. Else, colon, don't forget your colons, boy. Update the value of the variable val equal to the string okay. If the absolute value, the result of passing in the result variable set to the power p minus x into the absolute function is greater than the value of e at this point, then update the value of val equal to bad. Finally, print an f string in which there are replacement fields to format in x, p, and e's and val's final value in the output. And this will produce this shit. So, keyword arguments and default values. In Python, there are two ways that formal parameters get bound to actual parameters. In other words, there are two ways that parameters get bound to arguments. Why choose to use the nomenclature that is objectively, demonstrably more confusing? They both have parameters in the name. Why just not call one parameters and the other arguments like everybody usually does? Alright, sorry. There are two ways that formal parameters get bound to actual parameters. The most common method, which is the one we have used so far, is called positional. The first formal parameter is bound to the first actual parameter, the second formal to the second actual, etc. And by second, just the order in which they are written in the parentheses, when you define the function and whenever you call the function, that the first one in the tuple is assigned to the first one in the tuple in the other, right? Python also supports keyword arguments, in which formals are bound to actuals using the name of the formal parameter. In which arguments are bound, well, I guess it's saying no because you bound, in which arguments are assigned to parameters according to the name of the parameter in the function definition, is another way to say that. Consider the function definition. Define print underscore name, in which our formal parameters, aka parameters, are first name, last name, and reverse. Now, if reverse is true, if what is passed in as argument to here is true, right? If there's no other sort of explanation or condition, that's just what it means if this is true. Print last name plus a string, comma, plus first name, whatever's passed in to these parameters as argument. Else, print first name followed by last name without a comma. Okay, right, yeah, I see. I see what you mean. I see what's going on there. The function printName assumes that first name and last name are strings, and that reverse is a boolean, that either true or false. If reverse is equal to true, it prints last name, comma, first name. Because when we called the function, we said, it's true that what I'm giving you is in reverse, so reverse it, and do the Wells, comma, Michael. Otherwise, it prints first name, last name, Michael Wells. Each of the following is an equivalent invocation of print name. So we could invoke or call the function by saying print underscore name and then in parentheses the string Olga, the string Puchmajerova, and the boolean false. We could call the function with the same strings in the same order and then but pass in false as a keyword argument by specifying that we are passing in this argument for this specific parameter, reverse, by saying reverse equal false. We could call the function with the string Olga first, and then do the same thing as above, clarify and specify that Puchmajerova is as argument is supposed to be passed in to the last name parameter by saying last name equals Puchmajerova. I don't know if I'm pronouncing that right, I'm sorry. And same with reverse. But that's not usually how you would use keyword arguments because in this case you're putting them in positionally already in their correct order, so you don't need to specify them. But this is an example of where you might use keyword arguments. If you're not putting them in, you're not putting your arguments in the same order that the parameters were placed in the function definition. You can specify that this argument, Puchmajerova, is assigned to the last name parameter, even though you put it in first, same with the first name, same with your boolean value for reverse. Though, the keyword arguments can appear in any order in the list of actual parameters, it is not legal to follow a keyword argument with a non-keyword argument. It's kind of odd. But yeah, therefore, an error message would be produced by a function call which did so. Like here we pass in the last name argument as a keyword argument, and then we try to pass into reverse the boolean false as a positional argument. Can't do that. You just can't do that for some reason. It's illegal. You will get arrested. Keyword arguments are commonly used in conjunction with default parameter values. We can, for example, write this printName function in the definition of which we explicitly define the reverse parameter as equal to false. And the rest is the same. But this means, since we've given it a default value, this doesn't mean it's a fixed value. We can change that still whenever we call the function later, but if we don't pass anything in at all, then it'll be assumed to be its default value here. We don't have to pass in false every time that it's false. It will just assume such. Default values allow programmers to call a function with fewer than the specified number of arguments. For example, we could call it with just a first and last name, and it will function just like we called it with a first name, a last name, and the value false. Or, if we want it to be true and not false, we can still specify that in the function call. And here's an example of doing that again for some reason. The last two invocations of printName are semantically equivalent. The last one has the advantage of providing some built-in documentation for the perhaps mysterious argument true. More generally, using keyword arguments reduces the risk of unintentionally binding an actual parameter to the wrong formal parameter. Of unintentionally binding an argument to the wrong parameter. The line of code where both last name and first name are passed in as keyword arguments leaves no ambiguity about the intent of the programmer who wrote it. And this is useful because calling a function with the right arguments in the wrong order is a common blunder. The value associated with the default parameter is computed at function definition time. This can lead to surprising program behavior, as we discussed in section 5.3. Finger exercise. Write a function molt that accepts either 1 or 2 ints as arguments. If called with 2 arguments, the function prints the product of the 2 arguments. If called with 1, it prints that argument. So, in that case, like, you could set the second argument to have a default value of 1, so that in the function definition, like, even though it multiplies the first argument by the second argument, if you only pass in 1, then it just multiplies whatever you pass in by 1, thereby only printing that one argument that you pass in, yet working if you pass in 2. That's one way I think you could do it. I don't know. I'm not a professional, folks. I mean, I'm learning as I'm right along with you. Okay? This is why I'm doing this. I'm sure as hell not doing it for money. Oh boy. Variable number of arguments. Python has a number of built-in functions that operate on a variable number of arguments. For example, we've got a function, the built-in function min, to which we can pass in 2 arguments, 6 and 4, or more, as we see here when we call it with 4 arguments. And both of these are legal, and evaluate to exactly what you think they do. Python makes it easy for programmers to define their own functions that accept a variable number of arguments. The unpacking operator, ***, allows a function to accept a variable number of positional arguments. For example, say we define a function called mean, which has one parameter, *args, comment, assumes at least one argument, and all arguments are numbers, and returns the mean of the arguments. And in the function definition in the body, the variable tot set equal to 0, and for a in args, what's passed in as args, tot plus equal a. That is, update the value of tot to its own current value plus a. Have I talked about this plus equal thing before? This is equivalent to if you just said tot equal tot plus a. You can more conveniently just write tot plus equal a. And then return tot over len of args. And this will print out 1.5 and -1. What? How would it print that without any number passed in? Is that an error, or am I missing something? Whatever. Note that the name following the star in the argument list need not be args. It can be any name. Don't feel hemmed in. For mean, it might have been more descriptive to write mean star numbers. Because I mean, it's any function is going to have args. So don't just call it args. It's just terribly, terribly, terribly stupid. Scoping. Let's look at another small example, in which we have a function called f, which takes in one argument, x. It has one parameter, x. That just takes in one argument, colon. Name x used as formal parameter, which will set a variable y equal to the value 1. It will set x equal to its own value plus y, which again, you could type x plus equal y, and it would be the same, it would be equivalent. It will print a string x equals, followed by the value of x at this point, and then return x. Okay, so if we set x equal to 3, we set y equal to 2, and we set z equal to the result of calling the function f with the argument x, value of x used as actual parameter, as argument, we'll print z equals z, print x equals x, print y equals y, and when run, this code will print x equals 4, z equals 4, x equals 3, y equals 2. What is going on here? At the call of f, the formal parameter x is locally bound to the value of the actual parameter x, the argument x, in the context of the function body of f. Though the actual and formal parameters have the same name, they are not the same variable. Each function defines a new namespace, also called a scope. The formal parameter x and the local variable y that are used in f exist only within the scope of the definition of f. It is only in that space that that name means that thing, that is meaningful to mean that thing, and so outside of that function, you might use the same name. It's not referring to the same thing because it's in a different namespace, or scope. That's why I might be named Michael, and you probably know a million people named Michael. But if you look in your phone contacts list, find somebody named Michael, it's not going to be my number. It's a different, same name, different namespace. It's a funny way to put it, but it sort of makes, The assignment statement x equals x plus y within the function body binds the local name x to the object 4. The assignments in f have no effect on the bindings of the names x and y that exist outside the scope of our function f. Don't name your functions f, folks. Here's one way to think about this. 1. At the top level, i.e. the level of the shell, a symbol table keeps track of all names defined at that level and their current bindings. At 2, when a function is called, a new symbol table, often called a stack frame, is created. This table keeps track of all names defined within the function, including its formal parameters, and their current bindings. If a function is called from within the function body, yet another stack frame, or symbol table, is created. Three, when the function completes, its stack frame goes away. Vanishes, smoke on the wind. In Python, you can always determine the scope of a name by looking at the program text. This is called static or lexical scoping. Figure 4-5 contains an example illustrating Python's scope rules. The history of the stack frames associated with the code is depicted in Figure 4-6. So yeah, here, like they've used earlier, like injecting radioactive material into someone in order to be able to see the functioning of their circulatory system. They've included little print statements at different points along the way to clarify what value is assigned at what point to the same names. And it's a function f again with one parameter x, in the body of which another function is defined, g, with no parameters, and in the body of that function, x is set equal to a string abc, and then print x equals the current value of x is included, so that we know that if we see abc somewhere, then that's going to be, just you fucking get it, right? I'm not gonna keep going through that because I don't feel like it. And I think, folks, that's key to education and to learning anything and to growing and changing as a person. Just don't beat yourself up too hard. Stay interested. Follow your bliss. Don't make this into a masochistic exercise. It doesn't have to be. I learned a shitload of stuff without ever forcing myself to do anything I didn't feel like doing. The first column in figure 4-6 contains the set of names known outside the body of the function f, i.e. the variables x and z, and the function name f. The first assignment statement binds x to 3. Now this is interesting. I guess that's why they're called stack frames. The assignment statement z equals f of x first evaluates the expression f of x. I'm reading that like mathematical function. I mean, it means essentially the same thing, but yeah, it evaluates the expression, the function call of f with x passed in as argument, by invoking the function f with the value to which x is bound. When f is entered, a stack frame is created, as shown in column 2. You want to take another look at that? You can. The names in the stack frame are x, the formal parameter x, not the x in the calling context, not whatever's passed in as argument, right? G and h. The variables g and h are bound to objects of type function. The properties of these functions are given by the function definitions within f. When h is invoked from within f, yet another stack frame is created, as shown in column 3. This frame contains only the local variable z. Why does it not also contain x? A name is added to the scope associated with a function only if that name is a formal parameter of the function or a variable bound to an object within the body of the function. In the body of h, x occurs only on the right-hand side of an assignment statement. The appearance of a name, x in this case, that is not bound to an object anywhere in the function body, the body of h in this case, causes the interpreter to search the stack frame associated with the scope within which the function is defined, the stack frame associated with f, in other words. If the name is found, which it is, in this case, the value to which it is bound, 4, is used. If it is not found there, an error message is produced. When h returns, the stack frame associated with the invocation of h goes away. It is popped off the top of the stack as depicted in column 4. Note that we never remove frames from the middle of the stack, but only the most recently added frame, and that's part of why stacks are called stacks, is that you're piling things on top of one another, one after the other, then the last thing that you put on top of a stack is the first thing that you retrieve, right? Because of this last in, first out, LIFO behavior, we refer to it as a stack. Imagine cooking a stack of pancakes. When the first one comes off the griddle, the chef places it on a serving plate. As each successive pancake comes off the griddle, it is stacked on top of the pancakes already on the serving plate. When it comes time to eat the pancakes, the first pancake served will be the one on top of the stack, and the last one added, leaving the penultimate pancake added to the stack as the new top pancake, and the next one to be served. You get it, you know. Like this. Returning to our Python example, g is now invoked, and a stack frame containing g's local variable x is added, column 5. When g returns, that frame is popped, column 6. When f returns, the stack frame containing the names associated with f is popped, getting us back to the original stack frame, column 7. Notice that when f returns, even though the variable g no longer exists, the object of type function to which that name was once bound still exists. This is because functions are objects and can be returned just like any other kind of object. So z can be bound to the value returned by f, and the function call z with nothing passed in its argument can be used to invoke the function that was bound to the name g within f, even though the name g is not known outside the context of f. I gotta say, if you feel confused or lost at this point, I just understand it's just because when you explicitly write it out like this and the way that they're describing it, it's easy to get lost, but it's really a very simple and intuitive way that it works, and like if you will understand this just doing little things with Python very quickly, so don't worry if you feel lost at hearing it written out explicitly like this, especially because they're giving everything single letter names, and it's just all, it makes intuitive sense when you're using it. So what does the code in figure 4-5 print? It prints x equals 4, z equals 4, x equals abc, x equals 4, x equals 3, z equals the object function f locals.g at 0x1092a7510, or that would be different in your own computer, just this place in memory, and x equals abc. The order in which references to a name occur is not germane. That is, it's not relevant. If an object is bound to a name anywhere in the function body, even if it occurs in an expression before it appears as the left-hand side of an assignment, it is treated as local to that function. Consider the code, where we define another function that we call f, horrifically, which will print x. And we define a function called g, for some reason, that will also print x, but which, in the body of which, updates the value of x to 1. After we've defined these two functions, we assign the 3 to the variable x, we call f with no arguments, followed by updating the value of x to 3 again, then calling the function g. Now, it prints 3 when f is invoked, but the error message unbound local error, local variable x referenced before assignment, is printed when the print statement in g is encountered. Now what the hell's that for? Why is that? Come on. This happens because the assignment statement following the print statement causes x to be local to g. And because x is local to g, it has no value whenever the print statement is executed. Because now x has a name in this local namespace, and if we're looking for x, an object named x in the local namespace, there isn't one at the point in which the print is executed. It's almost like it goes back in time and says, oh, you're defining x as something within this local namespace? Well, then it will always be the case that you're looking for, when you call x in this local namespace, you're looking for a local namespace, x. If that was that helpful. Confused yet? Literally says that. Thank you. It takes most people a bit of time to get their head around scope rules. Don't let this bother you. For now, charge ahead. Start using functions. Most of the time, you will only want to use variables that are local to a function, and the subtleties of scoping will be irrelevant. In fact, if your program depends upon some subtle scoping rule, you might consider just rewriting to avoid doing so. Okie dokie, Mr. Smokey. 4.2 is also included in the readings for Lecture 7. Specifications. A specification of a function defines a contract between the implementer of a function and those who will be writing programs that use the function. We refer to the users of a function as its clients. Assumptions. These describe conditions that must be met by clients of the function. Typically, they describe constraints on the actual parameters, the arguments. Almost always, they specify the acceptable set of types for each parameter, and not infrequently some constraints on the value of one or more parameters. For example, the specification of find root might require that power be a positive integer. Guarantees. These describe conditions that must be met by the function provided it has been called in a way that satisfies the assumptions. For example, the specification of find root might guarantee that it returns none if asked to find a root that doesn't exist, such as the square root of a negative number. Functions are a way of creating computational elements that we can think of as primitives. They provide decomposition and abstraction. Decomposition creates structure. It allows us to break a program into parts that are reasonably self-contained and that may be reused in different settings. Abstraction hides detail. It allows us to use a piece of code as if it were a black box, that is, something whose interior details we cannot see, don't need to see, and shouldn't even want to see. The essence of abstraction is preserving information that is relevant in a given context and forgetting information that is irrelevant in that context. And Python is made entirely of highly abstracted stuff, makes it so very convenient. The key to using abstraction effectively in programming is finding a notion of relevance that is appropriate for both the builder of an abstraction and the potential clients of the abstraction. That is a true art of programming. Abstraction is all about forgetting. There are lots of ways to model this. For example, the auditory apparatus of most teenagers. Oh, some real boomer humor up inside this textbook, huh? Teenager says, "May I borrow the car tonight?" Parent says, "Yes, but be back before midnight and make sure that the gas tank is full." Teenager hears, "Yes." Am I right, folks? Haha, Shoto Jim. The teenager has ignored all of those pesky details that he or she or they consider irrelevant. Abstraction is a many-to-one process. Had the parent said, "Yes, but be back before 2 a.m. and make sure that the car is clean," it would also have been abstracted to simply yes. By way of analogy, imagine that you were asked to produce... Wouldn't the writer of the textbook realize that a large part of the audience is going to be teenagers? You have to be sort of condescending to the people. Anyway... By way of analogy, imagine that you were asked to produce an introductory computer science course containing 25 lectures. One way to do this would be to recruit 25 professors and ask each of them to prepare a 1-hour lecture on their favorite topic. Though you might get 25 wonderful hours, the whole thing is likely to feel like a dramatization of Pirandello's 6 Characters in Search of an Author, or that political science course you took with 15 guest lecturers. Bada bing! If each professor worked in isolation, they would have no idea how to relate the material in their lecture to the material covered in other lectures. Somehow, you need to let everyone know what everyone else is doing, without generating so much work that nobody is willing to participate. This is where abstraction comes in. You could write 25 specifications, each saying what material the students should learn in each lecture, but not giving any detail about how that material should be taught. What you got might not be pedagogically wonderful, but at least it makes sense. Pedagogy is the education of children, by the way. This is the way organizations use teams of programmers to get things done. Given a specification of a module, a programmer can work on implementing that module without worrying about what the other programmers on the team are doing. Moreover, the other programmers can use the specification to start writing code that uses the module without worrying about how that module will be implemented. Figure 4-7 adds a specification to the implementation of find root in Figure 4-3. Yep. The text between the triple quotation marks is called a docstring. At the top of the function definition, it's a multi-line string right here that explains what the function does. By convention, Python programmers use docstrings to provide specifications of functions. These docstrings can be accessed using the built-in function help. One of the nice things about Python IDEs is that they provide an interactive tool for asking about the built-in objects. If you want to know what a specific function does, you need only type help object into the console window. For example, help abs produces the text help on built-in function abs in module built-ins, new line, abs, parenthetically x, comma, space, / return the absolute value of the argument. This tells us that abs is a function that maps a single argument to its absolute value. The / in the argument list means that the argument must be positional. If you enter help with nothing inside, an interactive help session is started, and the interpreter will present the prompt help chevron in the console window. An advantage of the interactive mode is that you can get help on Python constructs that are not objects, e.g. help if, and then you'll get this handy expression or this handy explanation of the if statement. It'll even suggest related help topics. Interactive help can be exited by entering quit. If the code in figure 4-4 had been loaded into an IDE, typing help with find_root in the shell would display the name of the function, its parameters, and the docstring. The specification of find_root is an abstraction of all the possible implementations that meet the specification. Clients of find_root can assume that the implementation meets the specification, but they should assume nothing more. For example, clients can assume that the call find_root with 4, 2, and 100th passed in as arguments returns some value whose square is between 3.99 and 4.01. The value returned could be positive or negative, and even though 4 is a perfect square, the value returned might not be 2 or -2. Crucially, if the assumptions of the specification are not satisfied, nothing can be assumed about the effect of calling the function. For example, the call find_root with 8, 3, and 0 passed in could return 2, but it could also crash, run forever, or return some number nowhere near the cube root of 8. Figure exercise. Using the algorithm of figure 3-6, write a function that satisfies the specification. A function called log, which has 3 parameters, x, base, and epsilon, and which assumes x and epsilon are integers or floats, base an integer, and x greater than 1, epsilon is greater than 0, and power is greater than or equal to 1, and returns float y such that base to the yth power is within epsilon of x. Bada bing, bada boom.